I want to talk a bit about abstraction. It is a very important aspect of programming, especially when thinking about programming. In fact, it is one of the cornerstones of computational thinking, and I'd argue that programmers as a profession are some of the best at doing abstraction, as well as moving flawlessly between different levels of abstraction, even if they don't know what that actually means. Because not everyone understands the word abstraction. I remember this one time I asked a junior programmer to explain some of their code to me, and they started reading every line aloud, like, here it says if age is greater than 18, meaning that if the age is greater than 18. I stopped them and asked them to explain it a bit more abstract. They simply looked confused at me and said, my code isn't abstract, it's very concrete. Because of course, the word abstract is used to describe art like this. Art that is just a bunch of weird shapes and colors that doesn't resemble anything real. But it can also mean that you take a more simplified view of something, hide the details and talk about it in more general terms. Like in a game you're writing, if the user presses the A key, it moves the player to the left. That is one level of abstraction, a high level. What also happens is that your code subtracts some value from the X position of the player object. That is another lower level of abstraction. In this video, I'll take you through every level of understanding abstraction, from the very definition of the word itself, why abstract art is abstract, how abstraction makes comics more relatable, and how we all use abstractions in our everyday speech. And finally, through how you can improve the readability of your programs by making them more abstract, and how using abstractions will make you a better programmer. So no matter if you already know some of it, or are as new to the subject as the aforementioned junior programmer, I'm certain that you'll gain something from it. And I'll start with the word itself. What does it really mean that something is abstract? The Latin word abstraho means to drag away or draw away from, and abstractus means removed from, or rather drawn away from, if I get my Latin cases correct. It is very much related to the word extract, that mostly means taken out of another thing, whereas abstract more means taken away from another thing. It has been used by scholars and philosophers when talking about separation of the soul from the flesh, like abstracting from the bodily temptations to better concentrate on the purity of the mind. And it has been used to describe how we decide to ignore all the petty details of real life to better understand idealistic thoughts in politics and economics. Basically, to think in more abstract terms means to remove oneself and one's thoughts from the immediately observable, and for instance think about people as a concept rather than our neighbors John and Jane. So to talk about a program in abstract terms means to remove yourself as well as the explanation away from the code. For instance, if you have a program with code like this, you could explain it directly as computer code. If key is A, then player speed is subtracted from the player X, and if key is D, then player speed is added to the player X, in both cases setting player X to the new value. Or you can abstract away from the actual code and talk about what it does, what the user will experience. The user can move the player to the left or the right by pressing the A or D key. Both explanations are in a sense correct, but by removing oneself from the code, we get an explanation that can also be understood by someone else removed from that code. And that is an important reason for using abstractions. We don't want to overwhelm each other with unnecessary details. The word abstract means removed from, like abstract art, where the image you see is removed from the subject matter. This poster by El Lissitzky with the catchy title, Beat the Whites with the Red Wedge, and that is clearly also what the poster shows. Here's a red wedge, and if in doubt, it says next to it in Russian, Klenom, meaning wedge, and just below, Krasnym, meaning red. And here's a white bjelk circle that gets hit by. But there is a deeper meaning here. The poster is from 1919, in the middle of the Russian Civil War, fought mainly between the Reds, the Bolsheviks that wanted a new socialist state, and the Whites, which were a loosely allied army of, well, others. I'm not that well versed in early 20th century Russian politics. But anyway, the poster kind of shows the idea that a strong unified red drives a wedge in between the white forces, split them up, and probably wins the war. It was a propaganda poster, so could be interpreted both as something that had happened, something that was happening, or something that could or should happen. And it could be interpreted both as a literal army driving a wedge into an opponent, or as the idea of Bolshevism driving an ideological wedge into people's perceptions. Earlier artwork of military battles mostly depicted what an actual spectator might have seen, like dramatized depictions of the event. Here's an example from 1903, some 16 years before Lisitsky's poster, depicting a battle happening in 1815, about 100 years earlier. It almost shows the same kind of event, one army driving a wedge into another, albeit from the opposite perspective. Here we see the attacked army trying to defend itself and literally closing the gate on the attacking army. The painting is named Closing the Gates at Ouchemont. But the viewing experience is very different, where the poster takes the abstract idea of a wedge, and you have to imagine if the wedge and the circle are armies, people, or ideas. Then the painting shows all the details. Every single person can be identified. Their weapons, their uniforms, their facial expressions. Perhaps you can identify with the struggling redcoats trying to close the gate. Perhaps you can feel their frustration and fright and feel pride in their heroic defense. At least that was probably the intention of the painting. But you still have to build that perception from all the details. Of course, the image composition does a lot of the work. There is a pointy triangle driving in between two oncoming parallelograms here and here. They apply pressure on each side of that triangle, and another triangle of reinforcements is arriving from the right side. So you take all the details in and build an idea in your head of what is happening. You could say you'd have to extract the meaning from the observable reality. Just the opposite of this poster, where the idea has already been abstracted from whatever observable reality it might represent. And you're free to add any details in your head. Build the mental images that you deem most fitting. The two images represent two opposite directions to the same goal, either from details to a more generic idea, or from an abstraction to a more specific idea. Before going further with the exploration of abstraction in other media, including programming, I would like to take you on a short sidetrack and learn why this poster isn't actually categorized as abstract art. My initial research told me that this is suprematism, and since I didn't know what that meant, I went on a bit of a journey through early 20th century art history. And while I found it truly fascinating, after all, everything is interesting when you go into it deeply enough, I also realized that I can't possibly cover it in sufficient detail, so I'll limit myself to a few highlights. Everything always tracks back to Picasso, and with good reason. Not just because he made so many weird paintings with body parts all over the place.
Hey, here! Look! I'm Picasso! I don't get it.
But because he had a very good reason for doing so. the joke about not getting it is actually the whole point. Early in his career, he realized that he could never replicate the real world. No matter how realistic he could paint something, the painting would always be his interpretation of what he saw, and then the viewer would have to reinterpret the painting. So he decided to experiment with painting his interpretation instead, how he looked at the subject from various angles, imagining it as consisting of different geometric shapes. This is one of his early paintings in that style, and while it may just look like a bunch of shapes, you can also sort of see a girl playing a mandolin in there. But the more you focus, the girl seems to disappear and the shapes take over. In closing the gates at Ushimong, you subconsciously saw the triangles and parallelograms fighting. But here you have to interpret the painting consciously. You have to do some work to get it. Picasso inspired many other artists, and it became a whole movement that created a lot of paintings in this new style. The style became known as Cubism because of, well, all the cubes. At the same time, a different movement in the art world wanted to stop looking back at the past with all of its paintings of military battles frozen in time. It was called Futurism, and they wanted art to be focused on the future with all of its technology, action and speed. And like Picasso, they didn't want to simply paint what they saw, but to convey an experience, like using colors and shapes to form the idea of a speeding cyclist, rather than just painting a realistic still image of a cyclist. And some took to sort of combine the two. Cubo-futurism did paintings that used simple geometric shapes to convey motion and energy, and they wanted art to tell a story, to influence the future, rather than just depict the past. This is Kazimir Malevich, the knife grinder, and at first glance it might also look like just a bunch of shapes. But if you look closer, or maybe the opposite, let the painting fill your mind, you'll see that there is actually a figure there sharpening a knife on a rotating grindstone. I don't know about you, but I can almost feel the rotation of the stone as well as the movement of the hands. But Malevich wanted to go further and create paintings that were completely freed from trying to look like anything in the real world, but only consisted of geometric shapes. One of his most famous or infamous paintings is this, aptly titled Black Square. He named this new style Suprematism, and where Cubism was about interpreting the real world, Suprematism was about creating art that wasn't at all influenced by how the real world looked. As Malevich put it, to the suprematists, the visual phenomena of the objective world are in themselves meaningless, meaning that art should be art for art's own sake. The name Suprematism also says a lot about how far removed from the real world this art style is. The word supreme comes from the Latin supremus, which is the superlative of superus, what we know as super, and super simply means above, like Superman is above man and Super Nintendo is above Nintendo. So the superlative of super is the most super, the most above. Nothing can be any more above. But there are also other art styles that don't even use geometric shapes, but seem completely unrelated to anything known in the real world as well as in the ideological. So I'm not too sure that Suprematism truly is the most abstract style, but it doesn't really matter to us, because it turns out that this isn't actually Suprematism. It is in fact Constructivism, an art style that visually shares a lot with Suprematism, but where that wanted to separate itself completely from the real world, then Constructivism actually wants the art to represent something real, like the wedge represents the Bolsheviks and the circle the whites. And where other art styles interpret the real world into constructing the art, then Constructivism takes the opposite approach. It wants you to interpret the art and construct the real world. But we are not art historians, so why should we care? Well, the exact definitions and styles aren't that important, but keep in mind that there are all these different levels of abstraction, where art can be extremely close to how the world really looks. It can be somewhat abstracted to focus on a certain interpretation. It can be even more abstracted to give an impression of something more than is visible. It can extract completely away from the visible world to illustrate ideologies, or it can be truly abstract, seemingly without any connection to anything at all. And while this may also feel completely unconnected from the world of programming, I promise that it will soon make sense. After all, it does make a lot of sense in the world of comics. In his excellent book, Understanding Comics, Scott McCloud argues with an example of a human face that even as the art style moves further and further away from real life and becomes more abstracted and more simplified, it still seems real to us. In fact, he continues that the more it is removed from reality, the more relatable it becomes. A photograph is of a specific person, a detailed drawing is of a certain type, a simplified drawing is of someone from a group, and a smiley face could be any of us. It could be you, or it could be me. He goes on to discuss how the iconography of the cartoon makes it easier to relate to see the characters as oneself, and that it gets easier the more abstracted the image is from how real life looks. He then uses this for a further exploration of realism versus abstract art in comics, but I just want to emphasize his initial argument that when we abstract from the real world as it really is, we strip our subject down to the meaning, or at least whatever meaning we, the artist, want to convey. And as programmers, we are, after all, a sort of artists. The reason for abstracting isn't to remove all meaning, as abstract art sometimes tends to do. It is to remove specific and unnecessary details that might distract from that meaning in art, cartoons, language, and programming. Scott McCloud argues that words are the ultimate abstraction, that the textual representation of a face, the word face, is further removed from real life than any drawing, no matter how simplified. Not because there's a lack of details, but because there's no similarity, no connection between words and the things they represent. This in itself is an important aspect of language, this separation of word and meaning. But for now, I just want you to remember that when we write about something, we immediately abstract away from it. The written description is an abstraction. And in language, whether written or spoken, we don't just have the one abstraction, we have several different levels. One of the better descriptions of the different levels of abstraction was given by Samuel Ichi Hayakawa in his book Language in Thought and Action, first published in 1939 and updated multiple times since. And while you might think it has very little to do with programming, or at least very far removed from, I guess you could say abstracted from it, I want you to remember that a programming language is a language. A program consists of words that are abstractions of the actual operations that the computer performs. So allow me to stick with human language for a while, and afterwards you'll see how the same principles apply to programming. In the book, Hayakawa presents the ladder of abstraction and illustrates it with Bessie, the cow. When you're standing next to Bessie, you're on the same level as her, but as you climb the ladder, you abstract further away from her. You view her from a higher level of abstraction, and the higher you climb, the fewer details of the real world Bessie you retain. He then describes some of the different levels we can climb to when we communicate about or simply experience Bessie. At the lowest level is the collection of atoms that constitute this Bessie entity. But because everything in the universe is in constant flux, we can never actually perceive anything as it really is. Nothing is a static object, but a dynamic process. Thus, he calls that level the process level. It has an infinite number of details, more than we could ever know. So when we perceive Bessie, we are already abstracting. We are only experiencing the results of some of these processes. We see, hear, feel, smell only a small part of everything that process Bessie is. But to us, that is Bessie. However, when we talk about Bessie, like I am to you now, we abstract even further. We climb further up the ladder. Because the word Bessie is clearly not Bessie the cow. It is removed quite far from her, and if you have never perceived the same Bessie as I, you'd have no idea what that word meant. It is certainly an abstraction. So we have two different levels of abstraction, both abstracting away from the real Bessie, the process level. The first level of abstraction is the Bessies that we perceive, and the next level is the word Bessie. Let's say that you don't know Bessie, like at all. I could try to describe all the details that I perceive, but that would just be another abstraction, a different one than the word Bessie, and probably even more confusing to you. However, if I climb further up the ladder and explain to you that Bessie is a cow, then you'd have your own experiences of actual cows, not Bessie, but other cows, say Daisy or Rosie. And you'd understand what Bessie is. The word cow is a further abstraction. It removes all the details from the actual cows and only keep the general similarities they all have in common. But when we communicate on that level, we both know what is meant and are able to fill in our own understanding. I guess you could say that we both climb down our individual ladders to our individual perceptions of cows. But we can also go even further up the ladder. The levels Hayakawa describes aren't fixed or defined levels. He merely illustrates how we in daily communication often choose to climb higher or lower on this abstraction ladder, depending on what we wish to communicate. Because Bessie lives on a farm with other animals, the farmer would talk about all of them combined as livestock, whether it be horses, cows, sheep, goats, or pigs. When we climbed from Bessie to cow, we included all kinds of cows in our abstraction, focusing on what they had in common, being cows, and ignoring the details that made them Bessie, Daisy, or Rosie. Now we ignore all the details that make them cows, or sheep, or goats, and only focus on what they have in common, being animals on a farm. So when we climb up the ladder, we include other entities that wouldn't have been in the same group on a lower level of abstraction. When the farmer has to talk with the bank, he doesn't mention Bessie specifically, or indeed any of the other animals, but climbs even further up the abstraction ladder and talks about farm assets, combining animals with tractors, equipment, and buildings. Bessie is still there. She isn't removed, she's just abstracted away into something that is easier to talk about. And since the bank doesn't just deal with farmers, but with all kinds of businesses, they don't care about farm assets, but simply assets. Because the banker doesn't know how to buy or sell cows or tractors. He might never have seen a cow, let alone Bessie. But by abstracting her into an asset, he is still able to understand how she represents a value. So every time we climb up the ladder, we lose some of the details of Bessie. The real Bessie, process Bessie, still exists. We just can't be bothered with all the details all the time. In programming, everything is an abstraction. The spaceship of our screen isn't a real spaceship, it's just a drawing of one. And the enemies aren't our enemies, they're just different drawings that we score points by hitting. And those points are just numbers in the program. Heck, even the program itself is an abstraction. As Hayakawa describes, we cannot perceive the process busy, so we have to abstract somewhat away and simply talk about Bessie the cow. And as you now know, the moment we talk about Bessie rather than just experience her, we abstract even further away because now we have to use words. The same goes for programming. We cannot perceive everything that happens inside the computer, so we abstract away in our programming language. Hayakawa also argues that to be a good communicator, you need to operate on all levels of the abstraction ladder, moving quickly and gracefully and in orderly fashion from higher to lower, from lower to higher, and contrast it with what is called dead level abstracting, where everything is so abstracted that it becomes vague, ambiguous, even utterly meaningless. This can be seen in business meetings as well as with political candidates, where the words seem to have lost all connection with whatever meaning they once had. But also in tech journalism, whenever you read about the latest cyber attack, everything is so abstracted that you, as a somewhat technical person, have absolutely no idea what actually happened. Unfortunately, it can also happen in education, where some lecturers seem able to fill hours with abstract talk about concepts and ideas without ever giving you any understanding of how this relates to anything on a lower level or indeed in real life. So I better get into how this ladder of abstraction can be used in a very concrete way when it comes to programming. As mentioned, the program itself is an abstraction. Like any other language, it is just words. Words that abstract away from what actually happens inside the computer. And just like we can climb up the ladder and use different words that abstract even further in human languages, we can do similar things in programming languages. We can build functions, objects, modules, services, and so on, removing the details, not erasing the actual code, but merely moving it out of sight further down the ladder. Just like the banker doesn't remove Bessie out of existence by talking about her as an asset, we don't remove the code that does complicated calculations by putting it away in a function, but we do release ourselves from having to think about all the details all the time. In addition to organizing the code on a more abstract level, we can also simply talk about it in more abstract terms. And often we combine the two, because by talking about the code on a higher level of abstraction, we'll gain some insights in how to reorganize it and make it more abstract. And in fact, I'll argue that the more abstract the code is, the easier it is to understand, expand, and modify. But more on that later. First, let's try a very concrete example of making some code more abstract. Here's a simple little excerpt from a program. And while I probably wouldn't call it completely unreadable, it is fairly close. I mean, it's very hard to, at a glance, figure out what is supposed to happen here. But we can ask our junior programmer, who doesn't do abstraction very well, to explain it to us. First, we loop I from 0 to the length of the object's array, and then we say that if the square root of the ith element of the object's array's x value minus the other object's x value squared plus those two same elements y value minus each other also squared. If that is less than half of the ith object's w plus half the other object's w, then we multiply the array's object's value by 0.95 and subtract 1 from the other object's HL value. Yeah, I guess that is what the code does. But why does it do that? What is its purpose? Let's ask our more experienced programmer. Could you explain what this code does? Yeah. We loop through all the objects in the array, and then we calculate the distance from each one to our object using Pythagoras. And if that distance is smaller than the combined size or combined half width of the two objects in question, then we lower the S value by 5% and our object loses 1 HL point. Okay, now it begins to make a bit more sense. All this crazy math here, that's a distance calculation. The square root of the two distances x and y squared. I know that formula. It just didn't occur to me that that was what was happening. So let's rewrite the code to this somewhat higher level of abstraction. First of all, the loop itself is on a very low level with a lot of details specifying that it starts at 0, it ends at the last object, and it increments by 1 every time. But the programming language has another abstraction for simply saying that we should loop through all the objects in the list. So let's use that one. It's called for_off in JavaScript, and it requires us to make up a name for each object, a name to replace these object bracket I. And I'm still not sure what these objects are. So for now, I'll simply go with obj. It's not a good name, so I'll keep in mind that I have to rename it as soon as possible. But let's say for const obj of objects, go through all the objects in the list of objects, and then we can replace these with simply obj. And that one, and I forgot that one, and I don't know why everything turned red, but if I do this, it goes back. This didn't do much. But the next thing is, then we can take and abstract these calculations here. And we have two of them. This one, the first part, that was the distance between obj and object. So let's create a function called distance. Function distance that receives obj and object, and then it returns this exact calculation. The contents of the function is the exact same code as was here. We just replace this code with a call to the function. Like this. We haven't removed anything. We just hide the details here. We abstract them away. And we can do the same with the other calculation. This one here, that was the combined size. So we'll create a function called combined size of obj and object. And that should return exactly this. So we replace the calculation up here with the call to the function. Maybe you have already figured out what the code is really meant to do. Maybe even figured out what the next step should be. That just means that you're really good at abstraction. But for the rest of us, let's ask our senior programmer. What is the meaning of this code?
Oh, that simply checks if we collide with any asteroids.
Say what?
Yeah. It's part of this game where you control a small spaceship around the screen and have to avoid crashing into asteroids. And if you do, then the asteroid slows down and you lose some health.
So the array of objects is really an array of asteroids, and the object is really our spaceship.
Yeah. And they can all be interpreted as circles with the width as the diameter, and if two circles touch, they touch if their distance is less than the combined radius radiuses, and then they collide.
Okay, that certainly makes a lot more sense. So let's rewrite the code once more. First, rename these objects to what they actually are, asteroids and spaceships. Let's rename objects to asteroids. And this object here, that's the spaceship. And of course, obj, that would now be a single asteroid. The distance function and combined size function, they receive the asteroid and the spaceship, but they call them obj and object. Those are kind of bad names, and I could rename them to asteroid and spaceship as well. But truly, it doesn't really matter, as the functions are already at a lower level of abstraction. So maybe I'll just name them obj A and obj B to make it more clear that they are two different objects. Like this for distance and the same for the combined size. Okay, it looks a lot clearer now. Here, for each asteroid, we check if the distance between that asteroid and the spaceship is less than the combined size of the two, and if it is, then we do this. But we can climb even further up the ladder of abstraction. Remember what our senior programmer said.
That simply checks if we collide with any asteroids.
And although comparing the distance with the combined size will tell us if they are colliding, we wouldn't know that just from reading the code. So let's put that comparison into yet another function. And that function should tell us if they are colliding. If is colliding the asteroid and the spaceship. If they are colliding, then we return this, the result of this comparison. So we just remove it from here, put it into there, and then call the function up here. So now it becomes even more obvious what the program does. For each asteroid, if it is colliding with the spaceship, we do this. Those weird .s and .hl calculations still look a bit mysterious though. And what was it that our senior program said they did?
And if you do, then the asteroid slows down and you lose some health.
So let's abstract those calculations away as well. Create functions that are called slow down and lose health, like this function slow down. This should receive an asteroid, and inside of it does this exact thing here, and lose health should receive a spaceship and do this exact thing here. Maybe I should change this .s to speed and .hl to health, but for now I'll just leave them as is and let the functions themselves do all the abstraction. So all that happens inside the if statement will be that if the asteroid and the spaceship is colliding, then we slow down the asteroid and the spaceship loses some health. It is still the exact same code as before, in that the computer will perform the same operations when the program runs. But we have abstracted most of the details away, hidden them inside functions, and thus made this part of the program work on a much higher level of abstraction. And I think it's obvious that the program is much simpler, meaning easier to read and much easier to understand. I mean, it literally says what it does, what we have to have our senior developer explain to us. For each asteroid, if it is colliding with the spaceship, slow down the asteroid and let the spaceship lose some health. The extra cool thing is that if I, or indeed anyone else, at a later stage figure out another more efficient way of doing some of the details, for instance calculating the distance between asteroid and spaceship, they simply have to climb down into that function and modify the innards. The rest of the program doesn't need to know. Indeed, the rest of the programmers working on the same project wouldn't need to know all the details of how everything is implemented at the lowest level of abstraction. They can stick to their own rung on the ladder, just like the banker doesn't need to know anything about cows or tractors, but just assets. And that is truly the beauty of abstractions. What I need to do now is to go through the rest of the program and repeat this way of abstracting functionality into functions. I bet that somewhere there's a bunch of lines that deal with moving the spaceship around as the user presses different keys, and they could probably all be put in a function called move spaceship. And the same would probably be the case for the asteroids, so there could be some function called move asteroids as well. There's a lot of work ahead, and I'll put it all in a separate video that you can watch through the link up here or in the description. But don't watch it yet. Stay here for a bit of deeper dive into abstractions in programming. You might argue that the program hasn't become more abstract. On the contrary, it now looks closer to something we recognize from the world around us, so it feels more like the opposite of abstract. An abstract painting is hard to understand, but this code has become much easier to understand. That is because the world we have been abstracting away from isn't our real world, but the complex processes inside the computer. So the higher we climb the ladder, the less our code looks like, well, code, and more like stuff that we as humans know and understand. Remember the banker who abstracted Bessie into an asset. He doesn't know anything about cows or tractors or farms or houses, but he does know about assets. His world is built around those assets, and they make perfect sense to him, even though they are all abstractions of something he doesn't understand. So for him, an abstract asset is easier to understand than a less abstract cow. The same goes for us when reading the program. We understand asteroids and spaceships, and we have certainly experienced things collide, so we'll be able to work with and understand those abstractions, even if we don't understand any of the underlying code or indeed how the Pythagoras calculation works. So the more we abstract away from the code, the higher we climb the ladder, the less it looks like computer code and the more like real-world concepts. In a sense, it feels like the ladder should be turned upside down, or at least like we don't climb away from the real world, but more like we climb up from some deep, dark basement towards the light. And that is why I prefer another metaphor than the ladder, and instead imagine a diver in the ocean. The diver can freely move up and down between the surface and the ocean floor. So in a sense, this divides the world into three parts. The ocean floor is the bottom of our abstractions, the lowest level we can go. And for us programmers, that would be the programming language, or maybe even the framework, engine, or library we are using. We can think of this as the platform we are programming for. Like for a web application, it would be the web with the browser and the servers and all that. And for an app, it would be the operating system of that kind of phone, and so on. There might still be software below, but it usually isn't something we can change or even look at, and it certainly isn't part of our program. The water, the biggest part, is all of our programming code. When we are here, near the bottom, we are at a very low abstraction, like the example we began with, difficult to understand and a bit dark and scary. But as we swim up, we abstract more and more until we reach the surface. And the surface is then the real world, what we programmers also call the problem domain, because every program is a solution to some problem out there in the world. In our case, it is just a game, but it still solves the problem of letting the user steer a spaceship between some asteroids. And the idea with abstraction is to move the solution as far away from the platform and solution domain as possible and closer to the problem domain. But as programmers, we are divers that can dive through the solution, away from the surface, deep down through complex code, immerse ourselves completely in programming, at times absolutely forgetting about the problem domain until we need to get back up for air and see the program from the user's point of view. And if we don't like what we see, we dive back down again into the darkness, where the banker mostly stays on his rung on the ladder, talking about assets. We programmers have to move up and down through all levels of abstraction. At one point talking about asteroids colliding, then about Pythagoras calculations, then about function calls and return values. We move constantly because we can't possibly think about all the details all the time. So when we move up, we forget about some details, and when we move back down again, we remember them. And it is in fact a very useful ability. Imagine that we get a new task. It should also be possible to shoot at the asteroids to destroy them before they can damage the spaceship. This might seem like a daunting task, like where do we even begin programming that? Well, we start at the surface and express it as very abstract code, probably something like if is collision shot, asteroid, destroy asteroid. And that's it. Now all we have to do is swim deeper into those functions and fill in what must happen on the lower levels of abstraction. And in the next video, I'll show you exactly how to do that. For now, I just want you to understand that in art, comics, language, and programming, we use abstractions to ignore some details and focus on others. And depending on which details we want to focus on, we use different levels of abstraction. Each level moves us further away from what is actually there, but at the same time allows us to group more things, like to treat all kinds of animals as livestock. And while abstract art can be hard to understand and requires the viewer to actively work to get it, we use abstractions in our programs to make them easier to understand. We want to move as far away from the computer as possible and towards the problem domain to make our code less code-like and more real-world-like. We want to abstract away detailed technical solutions so we don't have to think about them all the time. Now I suggest that you watch my full video on improving the asteroid game with abstractions. There's a link up here and in the description. I invite you to download your own copy of the code and try to follow along. Instructions are in the video. And afterwards, you should try to do similar improvements on some of your own projects. Make the code easier to understand by making it more abstract. Oh, and don't forget to come back for the next video, Problem Solving with Abstractions. When it has been published, there'll be a link right here. See you soon, and have a nice swim.